Good morning, student. Today we will discuss abnormal molar mass and Van't Hoff factor. That means topic is abnormal molar mass and Van't Hoff factor. Van't Hoff factor is known as I, symbol is I. Abnormal molar mass and Van't Hoff factor. Before going to discussion regarding abnormal molar mass and Van't Hoff factor, we have to understand the two phenomena, dissociation and association. When a solute is dissolved in a solvent, solution is formed. Suppose solute is non-electrolyte, then there will be no problem. Numbers of particles remains the same before and after when the solution is prepared. But when ionic compound, otherwise we are using electrolyte as a solute in dissolving solvent to prepare solution, then the numbers of particles will be changed. That means we have to understand the first one is dissociation. That means dissociation. Dissociation, otherwise it is known as also ionization. Ionization. That means when electrolyte, otherwise ionic compound. That means electrolyte, otherwise ionic compound. When dissolved in water, then it will undergo ionization. Otherwise, dissociation occurs. Say example, ACl. When dissolved in water, then K plus and Cl minus. It undergo dissociation. That means K plus and Cl minus produce. Here one molecules of HCl, and from that K plus and Cl minus two ions are produced. Suppose similar with K2SO4, when dissolved in water, then 2K plus and SO4 minus 2. That means dissociation or ionization occurs both having same meaning. Then numbers of particles in solution increases. Here one molecules of K2SO4 one particle. From that 2K plus and SO4 minus 2, that will 3 particles are produced. From here 1, 2 particles, and here 1, 2, 3 particles are produced. That means when dissociation or ionization occurs, numbers of particles in solution changes and they are increasing. Now second is association. Association is completely reverse that of dissociation. That means in association, when a solute is dissolved in a particular solvent, generally the solvent having a less polarity, then the two or more molecules of the solute are combined and they form bigger molecules. That means they are associated and form bigger molecules. Therefore, this is known as association. That means, example, we can say when acetic acid, otherwise ethanoic acid, CH3COOH, okay, when dissolved in a non-aqueous solvent, that means suppose it is dissolved in a benzene having a low polarity, then two molecules of ethanoic acid are combined, CH3COOH twice. That means two molecules of acetic acid are combined and form one molecules. That means from 2 This is one molecules in which two molecules of acetic acid are combined. That means this is known as dimer. Two molecules are combined and form bigger molecules, then it is known as dimer. Suppose sometimes like this 3A, okay, and a proper solvent and form A3. That means three molecules of A are combined. This is known as trimer. That means when dissociation or association occurs, numbers of particle changes. In case of dissociation, numbers of particle increases. Here numbers of particle decreases. That means in case of association, numbers of particle decreases. That means colligative properties, which depends upon the numbers of particles, also changes. Because numbers of particles are changes due to dissociation and association, remember, and we know colligative properties depends upon numbers of particles. That means in this situation, that means when association, otherwise dissociation occurs in solution, then numbers of particles changes. That means if we are using colligative properties to calculate the molar mass of solute, that means we have more colligative properties: elevation in boiling point, depression in freezing point, lowering in vapor pressure, that means relative lowering vapor pressure, and the osmotic pressure. If we are using these four colligative properties to calculate the molar mass of solute, then this is not correct, because due to association, otherwise dissociation, numbers of particles changes. That means we are obtaining the wrong molar mass of the solute, and this is known as abnormal molar mass. That means when solute dissolve in a solvent and if solute undergo dissociation or association, then numbers of particles changes using colligative properties. To determine molar mass of solute, then it is known as abnormal molar mass. That means when solute dissolve in solvent, and if solute undergo dissociation or association, then numbers of particle changes. Now using colligative properties determine the molar mass of solute, then it is known as abnormal molar mass, because in this situation the molar mass which is obtained is not correct. So how to obtain the correct molar mass when association or dissociation occurs? Then we are using the Van't Hoff factor. So what is the use of Van't Hoff factor? The Van't Hoff factor uses to calculate the correct molar mass of the solute when association or dissociation occurs. Now this is Van't Hoff factor. How to define Van't Hoff factor? So as per definition, Van't Hoff factor is known as the calculated molar mass. Calculated molar mass of we are using molar mass of solute. So calculated molar mass divided by experimentally molar mass, that means observed molar mass. We can say observed molar mass. That means we can write MC calculator divided by M observed. Calculated molar mass, that means theoretical molar mass, observed molar mass, and then this experimentally molar mass, otherwise we can say abnormal molar mass. Also we can write normal molar mass. Calculated means normal molar mass. Upon we can write observed, that means abnormal. Abnormal molar mass. Otherwise we can write calculated, that means theoretical molar mass. Theoretical molar mass. Upon we can write experimental molar mass. All having same meaning. Now molar mass and colligative properties are inversely proportional. That means we can write from this observed colligative property. Observed colligative properties divided by calculated colligative property, that means theoretical. Calculated colligative property. That means experimental value of colligative properties divided by theoretical value of colligative properties. Otherwise, you can write like this: when a solute dissolving solvent undergo association or dissociation, then numbers of moles of solute after association or dissociation. That means numbers of moles of solute after association and for dissociation divided by total moles of solute before association or dissociation. All this formula having same meaning. That means by using Van't Hoff factor we can calculate. Now suppose we want to calculate the correct molar mass, then we have to change the, otherwise we have to change the formula of colligative properties. If we know solute undergo dissociation or association, then change in formula, that means change in colligative properties. So first one is we know P1 0 minus P1 upon P1 0 equal to X2. Second colligative properties, elevation in boiling point, that means delta Pg equal to Kd into M. Third one is delta PL equal to K into M. And the fourth one is the phi equal to CRT. Then if we want to calculate correct value, then we have to use the I. That means here multiply by I, Van't Hoff factor. Here also I. That means when solute is dissolving solvent, when it undergo association or dissociation, then use this formula to calculate the correct molar mass of the solute. Now solute undergo association or dissociation. It is not possible every time 100% association or dissociation occur. In this situation, we have to calculate the degree of dissociation and the degree of association. That means the degree of dissociation. Degree of dissociation, that means we can say alpha. The fraction of the molecules which undergo dissociation is known as the degree of dissociation. That means originally we have taken suppose 5 mole and from the 2 moles undergo dissociation, and then 2 by 5 is the fraction which undergo dissociation. Now in this situation, how to calculate the degree of dissociation? So remember, alpha equal to I minus 1 divided by n minus 1. Use this formula to calculate the degree of dissociation. Otherwise, if we know degree of dissociation alpha, then we can calculate I. Now I is one of factor. Now n. N means what? N means the numbers of particles which are produced by degree of dissociation. That means we can say here, in case of KCl, the value of N will be 2, and in case of K2SO4, N will be 3. That means what is N? The numbers of particles which are produced by when complete dissociation occurs of the solute. That means we can say for NaCl, N equal to 2. N equal to 2, suppose K2SO4. Then value of N equal to 3. This is the value of N. Now suppose we have Al2SO4 thrice. Then 5 will be produced. The value will be 5. In short, when solute undergo 100% dissociation, then the numbers of particles which are produced is called N. And if 100% dissociation occurs, then the value of I and N will be same, because at that time alpha will be 1. Now degree of association. Suppose symbol is X. Otherwise, you can also write alpha. Now, how to calculate X? X equal to 1 minus I n upon n minus 1. Now, this is I. What is n here? That means how many molecules of solute undergo association. That means suppose dimer. It forms dimer. That means 2 molecules are combined. Then the value of n equal to 2. That means for dimer value of n equal to 2. Suppose it forms trimer. Then value of n equal to 3. Suppose it forms tetramer. Then the value of n equal to 4. So by using this formula, we can calculate degree of association. Definition is same. The numbers of molecules of the solute. That means from that how many molecules undergo associated. That means the fraction of molecules that undergo association is known as the degree of association. Now, when solute is dissolved in solvent and there is no association or dissociation occurs, that means there is no need to use I, because in this situation the value of I is 1. And that means the value of I, one top factor, remember always one top factor I equal to 1. That means no association or dissociation. That means association does not occur, dissociation does not occur. Now I is greater than 1. When value of I is greater than 1, that means always dissociation occurs. And when I is less than 1, then always association occurs. Based on the value of I, we can decide association occurs, dissociation, otherwise no association, dissociation. Again, based on this, we can say here, suppose I equal to 1. That means calculated observed molar mass will be same. That means there is no association, dissociation. In case of dissociation, I is greater than 1. I is greater than 1. That means in this situation, observed molar mass will be always less compared to calculated molar mass, because I is greater than 1. This value will be smaller. And when association occurs, value of I is less than 1. So obviously this observed molar mass, otherwise we can say abnormal molar mass. Abnormal molar mass will be always comes greater than the actual molar mass, otherwise normal molar mass or calculated molar mass. So remember this value of I and the relation between the association and dissociation. Also remember formula of degree of dissociation and association. Use this formula when association or dissociation occurs. Then to calculate the correct molar mass of solute, use always I.